So yeah, the last thing we did before lunch was to look at the frequency response of the one-pole filter that we just created. And just to go back to it, so not 1, 0, 1 pole. There we go. Okay. So yeah, the frequency response of the one-pole filter is this frequency response. And as we said, basically those guys here are the teeth of the comb filter that we're creating, except that for now it's like very, very, very wide. And everything is very expanded, you know, and we can't really see the teeth of the comb filter yet because everything is after the Nyquist frequency. Okay. So what we're going to do now is that we're going to modify a little bit our Faust program so that we can add more than a one sample delay and look at the teeth of the comb filter in the spectrogram. So let's do this. So that was the code that we were, So here is the code that we were using this morning. And I removed the delay from the loop just because, once again, the loop creates an implicit one delay sample. So I'm going to put back delay again here. And for that, I'm just going to say delay. I'm not going to make it a fractional delay for now. I'm just going to use a regular delay. Here, we're not going to need a very big delay length. So I'm just going to set the maximum delay length to be 2048. Then I'm going to create a parameter that we will call delay length that I can change in here with a slider. I'm going to call that, okay, del length. The default value is going to be 1, the minimum is going to be 1, and the maximum is going to be 2000. I'm just going to say 2000 for now. Okay, and then a step of 1. And because I'm using, that's probably okay. I'm just going to leave it like that. So once again, I'm using a regular delay, so I can only set delay length as an integer, not as a decimal number. And that's fine for what we want to do now. So I'm going to save that, compile it, and there we go. So I'm going to look at the spectrogram of it. And okay, so for now, I'm going to set pretty high. There we go. Look at you. So I'm not going to be too aggressive. I'm just going to put it there for now. Okay. So what happened here is we have a one sample delay that adds to the one sample delay that we already have and that is implied by the feedback, right? And I can totally see that there is a peak here now. So it means that that's basically the first teeth of my comb filter that was moved here at the center of the spectrum, or like halfway between half the sampling rate and 0 hertz. Okay. And I can already hear that this is way more effective than the filter that I had before, right? Because now I definitely do get something that sounds almost like a sine wave, and that is basically this frequency that I have here, and that is...
Right now it's actually two
samples.
Two samples divided.
Yes. There we go. So now if I move to 4, now I got two very distinct teeth in my COM filter that just showed up. And so the more samples I will add, just like for the 1, 0, the more compressed the frequency response of my filter is going to be. And also the narrower these peaks are going to be. And because they're going to be narrower, they're going to highlight those frequencies even more, basically, because they're really going to isolate them. I'm basically changing also the bandwidth of the different peaks in frequency in the spectrum, highlighting more these very specific frequencies. And you can see that there are actually lots of them, you know, and I can go really, 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 really far with that. So now I actually have a real COM filter. And you'll notice that my COM filter, if I send noise to it, if the teeth are very, very sharp, which is the case here, I get something that is basically almost like a square wave, right? Because the harmonics are highlighted. And if I change the pole, it's going to become white noise again as I go toward 0. And on the other side, I also get a harmonic series, but it's just the opposite of the one that I had before, basically. So when I put a negative value to the pole here, the peaks are here, here, and here, and here. If I give it a positive values, the peaks are going to be where the gaps are right now, basically. So I'm just like shifting the whole spectrum. So now I really have a real COM filter. So let me just quickly check one thing. Yeah, there we go. Okay. So maybe before we do that, because I feel like it's after lunch, you guys are probably a little bit tired, your brain is probably very slow. Our next exercise after this one will be to modify the flanger that we had yesterday, so that instead of using 1-0 filter to do the flanging will be done here by the one-pole filter. And then it will be a real flanger. It will be way more effective than the one we were using yesterday. So that will be probably the next exercise than the one we'll do later. Before that, I'm going to quickly talk about physical modeling. Yes?
Show me the code.
Sure. So do you have any questions about that so far? I mean, it's pretty straightforward, right? All good? Perfect. So, that kind of filter is good to make echos. And in that case, actually, so we said that there are several kinds of filters, right? There are like low-pass filters, high-pass filters, band-pass filters that highlight a specific frequency. But this kind of filter that we studied here in a specific context can also be what we call an all-pass filter, right? And that's what we did with the echo. The echo is basically an all-pass filter because the whole thing is still considered to be a filter, right? Except that it doesn't remove any frequency, right? So in that case, we call our filter an all-pass filter, right? Do you have any other example of audio effects that can be considered as all-pass filters? Well, I guess, what? A delay can be probably considered as an all-pass filter. In some ways, a compressor probably, I guess, because compressor, a compressor doesn't change the frequencies. Like anything basically that doesn't change the harmonic contents of sound can be considered as an all-pass filter, basically, because it just let all the frequencies go through. Yeah, or gain. Okay, so the other thing that this filter can be is the simplest physical model of a string that you can have in the world. Okay. Why? So actually, it's interesting because CCRMA has a big history with that. Because what we're going to study now is what we call the Karplus-Strong algorithm. So, if we look at a string, this is a string. The string is being stretched between 2 points, 2 rigid terminations, right? Okay. So, when I introduce energy in the string, the energy, for example, if I introduce it here at the center, will travel across the string, okay? And then once it's going to hit the 2 rigid terminations, what is going to happen? Yeah, it's going to be reflected. And then it's going to travel back to the other side. And then it's going to become complicated. A lot of things are going to happen, a lot of interactions between the different waves. But the bottom line is that a string is basically a system where if we introduce energy, the energy travels in one dimension and gets reflected with a phase inversion on the 2 sides, right? So, in other words, this thing here is a -1 or a multiply by -1, and this thing here is a multiply by -1, right? So, a string and a room are basically the same things. If I take a room, like a weird room, like rooms like that don't exist, you know, but if I had a room where my room is just 2 parallel walls, and there are no walls at the bottom, so there is no floor, and there is no ceiling, so it's just 2 parallel walls, okay? It will probably sound like a string in some ways, or a little bit like a string, right? Because it's literally the same kind of system. The only difference is that in the case of the string, the waves are going to travel in metal or nylon or plastic or whatever, you know, while in the case of the room, the waves are going to travel directly in the air, right? So all these things are really connected together, basically. So one way to make a simple model of a string like this one is by creating what we call a waveguide. Okay. The way it works is that. So let's say that I'm adding energy here. And then energy is going to go that way, right? Boom. And then it's going to reach that point. How would I implement that? Just like the action of like having the energy travel from one side to the other of the string. How would I implement that with signal processing? No, for now, like just the fact of going from one side to the other of the string. Yeah. What is it? It's just delay, right? Because if I add energy in here, the energy is just going to travel, and it's going to travel at a certain speed. So it's basically a delay, because it takes some time to go from this point to the other, right? So I'm going to have a delay line in here. To go that way. So now, yeah, we're traveling that way, okay? Okay, then what about the waves that go from here to here? Because waves are traveling in both directions, right? Waves are traveling in this direction if they were reflected by this side, but they're also traveling in this direction if they were reflected by this termination here, right? So I'm also going to have another delay line, right? For waves going that way. So I have a delay line in here. There we go. There we go. Perfect. And that's for the waves going that way. So I have two delay lines, okay? So now I have the string itself, basically. Now it is a loose string. Now I need to have the terminations, right? How am I going to make the terminations? What? Well, that's the reflection here. So how am I going to make the connection between here and here, basically? How am I going to make the rigid termination of my string? Exactly. I'm just going to connect the output of this delay line to the output of this delay line. Okay? And then I'm going to have a phase inversion in here, which is the same as multiplying this by -1. And then, of course, I will have the same thing on this side. And I'm going to have another phase inversion here. So I'm going to have another -1 in here. Okay? And we agree that things are traveling that way, and that way, right? Isn't that cool? So that's actually a string. And it is not a very good string. It's not a very realistic string. Because there is a problem in my string. What is it? Absolutely. So if I send energy in the string, it's probably going to sound somehow like a string. The problem is that in the real world, when I send energy in the string and the energy travels in the string, you know, and is reflected, well, the energy in the string is dissipated, right, with time. I'm losing energy all the time. So the string itself doesn't really lose energy because it's very, very dense. Like very often strings it's metal, you know, so they are stiff and dense. So the amount of energy that you lose in the string itself is almost neglectable, basically. However, when the string is connected to a termination, a perfectly rigid termination doesn't exist, basically. So the bridge on the guitar and the nuts on the guitar are going to absorb energy, right? And by absorbing energy, they're going to remove this energy from the string. So we need to find a way to model that in here. How are we going to do that? Yeah, just like for the echo. Instead of multiplying by -1, exactly -1, I can multiply by something that is smaller than -1. And something that is typically going to be a number between 0.9 and 0.9999999. Okay? So some coefficient in here that I can call P. And same for this side. Okay? So that's what we call a waveguide. And Judah Smith, who will give you a talk tomorrow, is the person who found out about this. So he's a very good person to talk about this topic. Now, the thing is, typically, we can actually simplify this algorithm here by having only one multiply and one delay line, which is the same than what? If we only have one delay line and one multiply in this. It's the same as what algorithm that we studied today. Yeah, it's the one-pole filter, basically. Okay? So, yes, well, not in that case, yeah. Yeah. It's that's the feedback loop, absolutely. So, in order to do that, so basically the way this works here, right, is that here we can send energy, okay, and maybe we can have the output here, okay, and that's how we listen to this string in here, okay. So what we can do here, just to simplify the whole thing, is that we just assume that, all right, we've got a loop, okay, and this loop does what? This loop has delay, and the amount of delay in the entire loop is going to be what? It's going to be n plus n, right? Because it takes n samples to get there, and it takes n samples to get there, right? So then what I can do is that I can just have one delay line that is going to be basically z of minus n plus n, right? And then we have actually the right amount of delay in the entire loop, right? And then what about the multiplies that we have here for the reflection? Well, what we do in the case of the Karplus-Strong algorithm is that we only have one multiply. The thing is, because now there is virtually no proper termination, and that there is a sign inversion here every time, we remove the sign inversion in that case. Because it's like multiplying that guy by that guy here, you know? And now what we have is that instead of having a sign inversion, we have a positive coefficient. So the Karplus-Strong algorithm is basically going to look like that. Right? And that's a string. And that's basically the result is going to be the same as in here. And so it's going to sound the same, except that now we saved, well, we didn't save much. The only thing that we saved is like complexity just by looking at the algorithm, and we also saved one multiply. We didn't really save memory because the memory that we were using here got translated in here anyway. So we only saved one multiply. But trust me, in the 70s, that multiply mattered So this thing here is what we call the Karplus-Strong algorithm, or it's almost the Karplus-Strong algorithm because it's actually missing one little thing to become a real Karplus-Strong algorithm. So before we implement that in Faust, there is one last thing we need to do. So far, we've been considering our ideal length as a number of samples or as a duration, right? The thing is, ideally, what we want to do here is we want to consider our string as a frequency, right? Because we want our string to play a note, to play a specific pitch, right? So how are we going to tune our string so that it's going to play the right pitch? How are we going to do that? Then absolutely. I mean, how do you change the pitch of the string in the real world? I mean, there are basically two ways. It's either you stretch it more, okay, or you change its length. If you have a very long string, it's going to have a very low frequency, right? If you have a very short string, it's probably going to have a very high frequency. Oh, and look at that. Here we can actually change the length of our string by changing the length of the delay line. So we can have strings of many different lengths and just achieve many different frequencies, right? So now how are we going to calculate the length of the delay line that we need to achieve the right frequency for our string? So just as a reminder, what we can know in Faust is the sampling rate of something, right? And the sampling rate, for example, on my computer is 48 kilohertz. Okay? It's 48 kilohertz. So it means that I have 48 samples per second.
That's the ratio of the frequency to the sample.
Yeah, exactly. So if I had a string, it's a very short string. It was only one sample long. It's a very short string. What would be the frequency of the string? Yeah? Literally. So now we have a way to actually calculate the frequency of the string as a number of samples, right? So, so the way you do that is that, okay, let's say that what we want to know is basically n, right? So here I'm just going to say that this is n over 2, and what we want to know here is n. Okay, so it's the length of the delay line. So how am I going to calculate n? N is going to be equal to what? It's going to be equal. Exactly. It's basically going to be equal to the sampling rate divided by the desired frequency of the string. Right? It's as simple as that. And so now we can actually tune our string so that it has the right pitch, right? And going from there, knowing that the speed of sound in the air is, well, the thing is, here we're not really in the air, but we assume that we're in the air anyway. Like we could even calculate the length of the string, you know, like as certain size in meters or in inches, I guess. Yeah, so everything is very connected. So a delay is also a distance, right? Depending on the speed of sound and in the medium that is just. Absolutely. So that's pretty cool. All right, well, we pretty much got everything. Before we do it, one last question. So if we use a standard delay line, not a fractional delay line, not an interpolated delay line, what is going the problem of my string? Yes, it's going to be out of tune if I use high frequencies and depending on the sampling rates. So if I have a very high sampling rate, it's probably going to be in tune in the human hearing range, or it's going to be okay. You're not really going to be able to make any difference. But if I have a sampling rate of like 44 kilohertz, the string is really going to be out of tune for higher frequencies. So that's one of the cases where using a fractional delay line is extremely useful and is extremely important, because you want to have the same amount of precision for high frequencies than for low frequencies. With that, you have a lot of precision for low frequencies when you use integers, because if you use a very, very low frequency, like let's say 50 hertz, if you divide 48 by 50, you're still going to get a very big number. So you actually get a lot of precisions for low frequencies. But for higher frequencies, you're going to get less and less precision if you use an integer, right? So the string is going to be more and more out of tune as you go up in the frequencies. So that's why you need to make sure that this delay line here is a fractional delay line to still have the same amount of precision for high frequencies than for low frequencies. Okay? Very good. Okay, well, let's do it then. So here is the code. So what I'm going to do is, I'm going to just comment that out, kind of start over again, something new. Okay, I'm going to create a function that I'm going to call my string. Yeah, and it's going to be a virtual string. And what I'm going to do is that my string is going to have one parameter. It's going to be its frequency. So I want to be able to change the frequency of my string. Okay. So I will put a slider here later. Okay. Then I'm going to create the function myString. Okay. So myString is going to be very similar to the one-pole filter that we had here. Okay, so actually I can even just copy it and paste it in here. Okay. So the first thing I need to do is to change that to a fractional delay. Okay. Because I want to have enough precision so that my string is not out of tune. Okay. The other thing is, it is actually pretty important to have a very high order of interpolation here. So first order of interpolation is probably not going to be enough, or it might change a little bit the timbre of the string. So here what I'm going to do is that I'm going to say FDLA4 so that I have like a very high quality interpolation to get a lot of precision. Okay. So then I said that the sampling rate on my computer is 48 kilohertz. I seriously doubt that I will play a note below 50 hertz with my string, right? So if my sampling rate is 48K, and if I divide it by 50 hertz, then this will be the maximum delay length that I will have. And the nearest power of 2 of that is 1024. Very good. So I'm going to set it to 1024. Okay. here I got the delay length. I'm just going to leave that, and here I don't need the minus sign anymore, and I'm going to change its name, so that I'm just going to call that feedback for now, and we'll actually change that later. Okay. So now I need to create a parameter for my string, and the parameter is going to be the frequency of the string. Okay. And what I will control with the frequency parameter is the size of the delay line that I'm using the formula that I just showed there. So what I'm going to say is that delay length is going to be equal to the sampling rate over frequency. Okay? And because I'm going to do things in a clean way, I'm actually going to declare feedback in here because it would be kind of weird to put user interface elements in here and part of it outside of the function. Just, you can do it, but here I'm just implementing a string. And this string has parameters. Okay? So then what I'm going to do is that I'm going to declare two variables here that are going to be controlled by sliders. So I'm going to have a horizontal slider to control the frequency. I'm going to call it freq to respect Faust standards. Frequency, okay? And then I'm going to say that the frequency, well, the lowest frequency, I'm going to say it's going to be 51. The default frequency is going to be 440 hertz. And the highest frequency doesn't really matter, but I'm going to say 2000 hertz, for example. And a step of 0.01. And then I'm going to create the feedback. And it's also going to be a slider. And that one I'm going to call it feedback. And its default value, I'm going to say 0.9. Minimum value 0. Maximum value 1. I'm going to play with fire. And a step of 0.01. Now I plug the frequency to the string function as well as the feedback. There we go. I got my algorithm. The what? Feedback. Oh yeah, thank you. So there is a problem here. What is the problem? So it's just, it's more like for aesthetical reasons. I did it because I called this function my string. So it's a string function, so it'd be kind of weird to have the user interface elements in the string, so I'm declaring them outside of the string. So, but there are no, it's more like an aesthetical reason than anything else. Yes?
Did you say it was an aesthetic issue?
It's what?
Did you say it was an aesthetic issue? Or,
It's more, yeah, it's for the beauty of the code.
sorry.
And the 4 at the end of the F delay, what does that mean again?
It's basically the amount of precision of your delay line.
Okay.
So if you only have F delay, then you have a delay line that has floating point precision, so decimal level precision, but it's not very, very precise. If you say 2, it's more precise. If you say 4, it's even more precise. So yeah, careful guys, because here we're doing dangerous things. So there is a problem here. And the problem is the following. So actually I'm going to save that. I'm going to recompile it. This string is not going to make any sound. And there, can someone tell me why it doesn't make any sound? Yes, because there is no one to pluck it. And so I have the string, but I don't have anyone to plug the string. So actually what I can do just for fun, I can actually connect the microphone of my computer to the string. And so if I increase the feedback, not too much, right? So it kind of sounds like a string a little bit, you know, except that for now I'm just like controlling the string by blowing in it. So it's not very good. So what I'm going to do is I'm going to create a virtual performer to drive my string. And it's going to be a very shitty performer. So how can I just drive my string? What is the best way to drive it? Yeah. So like, I mean, we can improve that in many ways, but one simple way to do it is just sound an impulse in the string, you know, like, just like a pop. So, and I want a user interface element to do it. And this user interface element, well, it's going to be a button, right? So I'm going to create a gate. And I'm going to say button, and then I'm going to say gate, okay? And so what I'm going to do is that for the minimum value of that, I'm just going to say 0.9, because that will be more practical to change the value of the slider. So now I have a button. So all I want to do for now, because the button is going to create a click, right? When I press the button, it's going to do tuck, because it's going to go from 0 to 1. And because in Faust, everything is a signal, I can use my button to actually send a signal to my string. So I'm going to say gate here, and I'm going to connect gate. So I'm going to connect my button to my string. Okay. Now I'm going to save that. And there is an error. Yeah, it's because I forgot to put quotes here. There we go. Okay, so now I got a button. So we have gate, okay? What I'm going to do is that I'm going to create a new function. And this function, I'm going to call it impulse, okay? And my impulse function is going to take gate as a parameter, okay? And I'm going to replace that by impulse in here. Very good. So what I'm going to do is that I'm going to split the signal of the button into two signals. One, two, and one of them I'm going to delay it by one sample. And then I'm going to subtract them together. Okay? So now what happens is that when I press the button, okay, so the button is pressed. So when the button is pressed, I go from 0 to 1, okay? So here I have 1, but the previous sample I had 0. So 1 minus 0 equals 1. Good. But then at the next sample, my gate is still outputting 1, right? So then I'm going to have 1 minus 1, 0. Good. All right. It's better. Then I have a problem. exactly. The problem is that when I release gate, then gate is going to go from 1 to 0. So then I'm going to have 0 minus 1 equals, yeah, and then, well, I mean, we're going to do it anyway for now, because now we should have cell. So there we go. Nice. So actually what I'm going to do is I'm going to put that back the way it was. Very good. So now I have a string, and I can control the duration of vibration of the string just by changing the feedback. So it works. Very good. So you see that my simple physical model that I had here works pretty well, you know, because I got the feedback, and the feedback is definitely changing the time of vibration of the string. So the feedback is really controlling the damping of the string. Okay. So now the problem is that when I click on gate, I got an impulse that is a positive impulse when I click, and when I release it, I get an impulse that is a negative impulse, which doesn't change anything, because it's just that they have a different phase, but that's fine. At the end, it's not a problem. So now that I'm doing that, I'm gonna have to add one more step to make sure that this doesn't happen. Because I only want the excitation to be sent when I click on the button, right? Not when I release it. How am I going to do that? That's a little bit trickier.
Is there a max or a min?
That could be one way to do it, but there is an even like simpler way.
Bigger than 0. Is there an operator?
Absolutely. You're good. So what I'm going to do is that at the end of that, I'm going to add one more step. And the new step that I'm going to add is just going to be greater than 0. Okay? So greater or smaller or greater or equal or smaller or equals are the same than in C++, and you can use them as standard Faust operators with the parentheses, you know, just the same way than all the other operators in Faust. So now what happens is that the output of this operation sometimes is 1. Sometimes it's 0, and sometimes it's minus 1, right? So if I do that, in the case where I create my click and I get a 1, then if I have 1 greater than 0, it's true. So the output of that is going to be 1, because the result of this comparison is also a signal, because in Faust everything is a signal, right? So the result of this operation here is going to be 1. Okay? Then if I send 0, I'm going to have a 0 greater than 0. No, 0 is not greater than 0, so the result of the operation is going to be 0. And then for the minus 1, same thing. Minus 1 is not greater than 0. So I'm getting rid of my minus 1. So now the only thing that is going to be outputted by this is going to be 0 or 1, basically. So I save it. I click. And now when I release the click,
So if it's false, it sends out 0.
yes, if it's false, it outputs 0. If it's true, it outputs 1. So when I click, I just get like, there we go. Yeah, look.
Just to be a perfectionist, can we put a minus 1 in the delay length?
A minus,
Since there's an implied sample delay in the feedback. Either in my string, but delay of -1.
It's a very good point. We should do it, actually. No, you're totally right. That is a very, very good point. Because right now, our string is probably a little bit out of tune. Just a little bit. I mean, it's probably like, even if you have perfect pitch, it's very unlikely that you hear it. But that is a very good point. So what Luc is saying here is that we should take into account that the feedback here implies a one sample delay, right? And so we should subtract this one sample delay to the delay length that we calculated in here because it's already in there basically, right? So that is a very good point. Good. All right. So before we move on to the next topic, we're going to make another improvement to our algorithm. So right now it sounds like a string, kind of. But it's not a very realistic string. How can I make it sound more realistic?
Add a reverb?
So, no, but actually it's a very good point. That's a very good point. That's what, so exactly. No, but that's a very good point. That's you know, that's in general that's what students who didn't do a lot of things in their homework do to make it sound better in general. That's and it works. It's very, very effective in general. So yeah, adding a reverb would be a good idea. It would definitely make it sound better. But to make it sound more like a string, because adding reverb will probably make it sound maybe a little bit more realistic. But to make it more sound like a string, what could we add? What would be the next step? Because our physical model, our so-called physical model, here is missing something that happens in the real world. So that could be the step after this step. But there is one before that that will make things even better.
Low pass filter.
Yes, that's it. So, I mean, there are many things that we could do here to make it sound better, like because it's a very, very simple model. But in the real world, what happens to the string? So, back to the string that we had here, okay? So when the wave travels, hits the termination, it is reflected with a sign inversion, and it's losing energy. The problem is that it's not losing energy linearly across the spectrum of the sound, right? Oh, it's losing high frequencies first and lower frequencies after that, because lower frequencies have bigger impedance, you know, so high frequencies are discarded first, you know, and lower frequencies last, okay? So our bridge and our nuts here are frequency dependent, right? So, so an improvement that we can make to our little system that we have here is that instead of removing the energy linearly across the spectrum of the sound by just doing a multiply, we could actually apply a low-pass filter in here to remove high frequencies first and lower frequencies last, right? Does that make sense, or? Okay. So, in the traditional Karplus-Strong algorithm, or if you read the Karplus-Strong paper from the 70s, the way they did that is in a very, very basic way. You can make that in a very complicated way. You can design extremely fancy filters to do that so that it's going to really sound really realistic. But the way they did it in the 70s was basically by just having a very simple 1-0 filter. So a feed-forward filter that we also call a moving average filter, as Luke said this morning. So that's what we're going to do here. What we're going to do is, at this point here, in the feedback, so we have the feedback, and what we're going to do here is that we're going to add a new step. And in this new step, we're going to design a very, very, very basic filter. And this very, very basic filter is basically just going to be the signal added to the signal delayed by one sample. Okay? I'm going to have to put parentheses. Divided by 2. And that's how they did it in the, like, all one. Because then, that's a low-pass filter, right? Because that's our feed-forward filter. We're adding the current signal with a delayed version of it by one sample. Okay? And then we're dividing it by 2 here. Why? Yes, so that for low frequencies, we don't increase the gain. Okay? And that's very important, because here we're in a feedback loop. So if we increase the gain of the signal in it, it's going to become unstable and it's going to blow up. So we have to be careful in here. So now if I save it, yeah, well, there is a problem here. Can someone tell me what the problem is? It's not happy. I know what the problem is, but can someone see what the problem is? No? Emma? Yes. Here I have 2 signals. 1, 2. The problem is that the output of this thing is only 1. So I need to split the signals. Does that make sense? Or yeah. So I'm going to save that. It's compiling. Ah, that's more like a string.
And if the button you also pass it through a low pass filter, it gives you a more less abrupt blinking of the string. Would that help?
To do what? Sorry.
If the gate,
Yeah.
the impulse, which now is a very sharp pulse, if you put a softer pulse, will that help or not?
Yes and no. That's not the best way to do it. The best way to improve that would be to have a noise generator and apply an envelope on the noise generator so that the excitation that it creates sounds like instead of that would make it sound better. But then if you want to do that, it gets more complicated because then you actually need to make a real model of plucking that's a little bit more complicated. Like the next improvement that we could do on the excitation would be that instead of using an impulse, so just a direct like a tack, we could have a noise generator and apply a very short envelope on it so that the excitation is just a and then that would improve the sound. We're not going to do it because we don't really have time for that. Any other question? So this was used a lot, like heavily. And especially here. That's the thing, yeah. So there is this composition by David Jaffe called Silicon Valley Breakdown from the 70s, and you should. There is a video on YouTube of it. You should look at it, and the video only uses that, and it really sounds like that, So the entire composition is just based on sounds like that, and at that time they were like trying to explore what they could do with it, and that was like in the early 80s. Yeah, early 80s. So, 10 years before I was born. I'm saying that because Nando was already there. So that's anyway. So yes. So the bottom line here is that this is the very, very, very fundamental things that you can do for physical modeling. Modern physical models of musical instruments, like commercial one, the one that you use in commercial synthesizers are pretty much all based on something that looks like that. It's more than that. It's way more than that. But the core of it is basically that. And that's a family of physical models that we call waveguide physical models. And there are several ways of doing physical modeling. This one is not the most accurate one, but it's by very far the one that sounds the best. And that is the most efficient, and that is the easiest to deal with. And that's why it's the one that is used everywhere.
So why does it sound the best when it's not the accurate? So how come?
So it's a good question. So you have three main ways to do physical modeling. The old way, which is probably the most accurate way of doing it, is called the finite element way of dealing with physical models. And in that case, you take an object like this pen here, and you basically create a transfer function that is going to model the behavior of the pen, depending on the the material it's made of, like its thickness and et cetera, et cetera. And that's how people made the first physical models. And that's how some people still make physical models. For example, there is this great book by Stefan Bilbao. I don't remember what the name of the book, but Stefan didn't write a lot of books. So if you Google his name and if you look for Stefan Bilbao's book, it's probably the one. So there are still people who do that. The problem with this method is that it's extremely computationally intensive because there are a lot of things to. I mean, the transfer function of this pen is a fancy one. It's a huge transfer function. It's so huge that we've only been able to compute them on computers like only for maybe the last 7 years, like that kind of computer in real time. So it takes a huge amount of processing power. And the other thing is that it doesn't sound that good too, because it's very often an approximation of what it actually is in the real world. So a lot of computation, it doesn't sound that good, but it's more accurate, physically speaking, than a waveguide physical model. So that's one method. Then there is another method. The other method is based on what we call the mass and spring paradigm. So the idea is that you model an object with a mesh of masses and springs. So this sheet of paper, for example, is just a mesh of masses and springs. And when I strike it, the wave travels and the masses moves, and they are connected to each other by strings. By springs, sorry. And that's another way to do physical modeling. So that one is a little bit more computationally efficient than the finite element one, but it still doesn't sound very, very good. The beauty of the waveguide technique is that you only have one multiply in one little line. And here you go. You have something that already sounds better than any finite element physical model from the 70s or mass and spring model that would require thousands of multiplies. So, so that's the thing. All right. While we're talking about physical modeling, there is one thing I want to add to that. I'm talking about that because physical modeling is kind of my field. So the physical modeling is great. The big problem of physical modeling is that you can have the best physical model in the world. If you don't control it in a good way, it's not going to sound good. And on another hand, if you have the simplest physical model in the world, like this one, if you control it the right way, it's going to sound great. And by controlling it the right way is that if you just send MIDI informations to it, it's not going to sound good. Why? Because here we're really dealing with physical objects. Okay? In the physical world, if you take a clarinet, okay, and you play the clarinet player instinctively is going to control hundreds of parameters on the clarinet, especially in the mouthpiece. For the tone holes, he's not going to control a lot of things, right? So it's going to be like, well, on the clarinet, a little bit more, though, because on the clarinet, you can definitely, let's say a saxophone. Saxophone is probably better because the saxophone, it's basically closed or open, and that's it. And there are not a lot of effects that you can create just by half opening the tone hole. Okay. So with the fingers, you don't control a lot of parameters because the only parameters that you control are basically, you know, like change the note, right? Then in your mouth, there are a lot of things going on there. And like instinctively, you're going to change the position of your mouth compared to the mouthpiece every time you're going to change the note. And your brain is going to learn how to do that. And that's why it's going to sound terrible when you're going to start playing saxophone. It's going to sound better once you're going to get good at it. It's because you will learn how to change very little parameters in the mouthpiece so that it's going to sound good. Here, if I have a great physical model, very accurate physical model of a musical instrument, if I don't do that, if I don't change all these parameters the same way than a real saxophone player would do it in the real world, it's going to make sound, but it's going to sound like shit. It's going to sound like a 3-year-old taking the saxophone and just blowing into it, you know? And it's the same for a violin. It's even worse with a violin. Like with a violin player knows exactly what to do, like what movement to have to create exactly like this very specific sound. If you have an excellent physical model of a violin, if you don't control these parameters exactly the same way that a violin player would do it, it's going to sound terrible. And that's the main drawback of physical modeling. And that's why physical modeling, probably one of the reasons why physical modeling is harder to deal with than sample-based synthesizers, because with a sample-based synthesizer, you don't have to worry about all these problems. Then there were works by people to try to solve these issues. For example, there was this postdoc student here at CCRMA called Esteban Mestre, who comes back here very often. And Esteban did his PhD thesis on that, on controlling physical models with where the user provide very high-level informations and where there is some kind of mapping system in between that is going to turn these high-level informations into informations that the physical model can use to be played in the right way. but it's complicated. It's very, very, very complicated. And another thing, and then it's more like my personal point of view about physical modeling, is that if you, it also depends a lot on the interface that you use to control it. Because the problem is that if you try to control violin with a piano keyboard, you're losing a lot of stuff there, because the problem is that a piano keyboard doesn't work the same way than a violin. So you're losing a huge amount of information there. So if you want to have a successful controller for a physical model, in some ways it will have to be a little bit close to what the actual model is in the real world, because otherwise it's probably not going to work very, very well.
But how about developing a robot that will take, a device that looks like a wind instrument and maybe...
Sorry, can you speak a little louder? I'm
Yeah,
curious.
I'm suggesting that maybe a development of a robot that simulates a human that plays the wind instrument is more easy. Is easier? I don't know.
Not really, though. Like the thing is, so there were a lot of people tried a lot of things to solve those problems, and one of the way people solved this problem, or tried to solve this problem, in the 90s, Yamaha released this keyboard. You can see downstairs the VL1, which was a physical model-based keyboard. So all the sounds in this keyboard are based on physical models of musical instruments that are all using this technique. Yes. And that was part of a patent that Stanford, that Karma had with Yamaha in the 90s, basically.
No samples, everything.
No samples, yeah. Everything is computed. So no samples. And the way... So if you were playing like a piano sound, for example, then you had a piano physical model, but you were playing it just like a piano. If you were playing a wind instrument, you actually had a wind controller. So you had this little thing that you were putting in your mouth, and you were blowing in it, And this thing was also measuring the amount of pressure that you were applying with your mouth on it. So you could beat it, and then Yamaha just developed a big series of controllers that are using that. I think Daniel used one of them, right? And I always forget the name of it.
UX5.
Yeah.
Is it the current incantation?
Oh,
Yes.
There's a Swedish company that makes a really cool, cheap USB controller that is, you put it in your mouth and blow into it. It's really great for playing the STI. It's tecontrol.se.
Yeah.
It's really good stuff. I have it.
So yeah, there are ways to deal with that, because then you change the pitch with the keyboard and you do that, and then you have a weird.
The funny thing is, so what makes a violin, right? It's like a 440, right? An A on the violin, an A on the piano. It's essentially the format, right? The difference is it's the thing that is forming the thing that's going to vibrate at that frequency at the end, right?
Sure.
It seems funny that if you hand a violin to, I don't know, like a kid, right? A violin and a MIDI controller, right? Both are going to sound terrible, right? People are good at the violin because they work so much on the violin, right? I bet if you had like great controllers for that, for like Faust, right? And people spend the same amount of time with that controller, at the end of the day, they probably would make sounds that are just as good as the violins make on the violin. We're in this backwards phase now trying to emulate stuff, but I think we're going to go beyond that very soon. There's nothing magical about the physical things. It's just
Oh, no, sure. Well, the only thing about... No, I totally agree with you. But the only thing is that physical things behave in a physical way. And in general...
So do the speakers that are outputting what that is doing, right?
Sure, but the thing is that if you make a synthesizer that is like a purely electronic synthesizer, and even though like it has many parameters that are controlled in real time, and changed in function of what you play, if you press it, it's still going to sound like a synthesizer, right? Well, a physical object goes between so many stages while it vibrates, basically, that there is a lot of complexity in it. And it's basically producing like all these transients, all this complexity, all this stages, you know, like going from this stage to this stage to this stage that is that is good basically, and that people are used to it. And
but again, 99% of the violins sound like crap. Only the good instruments that people take a lot of effort.
Sure.
The good ones sound well, right?
Absolutely.
Software, I want to say.
No, sure. No, you're totally right. So, so it's funny because physical modeling has always been a pretty, I wouldn't say controversial field, you know, but there are a lot of people who talked about physical modeling, you know, especially in the 90s, you know, where people were okay, we're gonna make a guitar that is like 1 kilometer long, you know, and it's gonna have very gigantic strings, you know, and it's gonna sound totally crazy. The problem is that you can do it, you know, but you can extrapolate. You can do more with physical modeling than what you actually have in the real world. The only thing is that what people kind of forget is that if those things don't really work in the real world, because there are physical models of real things, it's also a little bit hard to make them work in the virtual world too. And even if you have a gigantic guy who's plucking the Golden Gate Bridge to make music with it, is it going to sound good? Or is it going to, I mean, it's certainly going to sound like something. It's probably going to sound very low because those are pretty big strings, you know. And but it's so I think there are a lot of people who are trying to find a good compromise between these two worlds, you know. But I think physical models are very important and they are very good, you know, and they are still probably somehow the future, you know, just because you can make them very easily, and they behave like things in the real world. And because they behave like things in the real world, a lot of features that are musical features come for free with them. If you have an analog synthesizer, if you want to change the timbre of the analog synthesizer, you have to touch like many buttons at the same time in order to be able to do it. With a physical model, all these things happen for free. You don't have to change the parameters in real time for them to happen. And I think that's why physical models are definitely still very successful. Yeah. So, any other questions? So one thing I want to mention here is that this physical model that we have here is a physical model of a string. It's also a physical model of a tube, because a tube works exactly the same way than a string. So if we had to make a physical model of a clarinet here, it would be very straightforward to do it, because a waveguide, so this thing here is also a tube in a way, right? Because if you have a tube, that's the tube. If you send sound in the tube, if you just send an impulse in here, boom, then the sound is going to travel across the tube, just like in the string. Then it's going to be reflected, etc., etc., etc. Okay, it's going to be reflected, but one quick question though. In general, if you have a tube, the tube has an open end on both sides. Why is it reflected then? There is an open end. What?
I said, I've always wondered that, yeah.
So it's because of the pressure difference between inside the tube and outside the tube. The wave that you create and that travels in the tube, okay? So the traveling wave in the tube is a compression. So it's high pressure. And then outside of the tube is lower pressure. When the high pressure wave is going to hit the rail, like the air outside of the tube, then this difference between the high pressure and the low pressure is going to create a bouncing back in the tube, basically. And so it's the pressure difference between the wave traveling in the tube and the air outside of the tube that creates the reflection. And I don't know if you've noticed, but many musical instruments end up with a horn, right? And there is actually an acoustical reason for that. I mean, you don't need it, but there are several acoustical reasons for the horn. But one of them is that this is actually going to stabilize a little bit this process, because then the transition between the outside and the inside of the tube is a little bit smoother, and it's going to increase this effect, and it's going to stabilize a little bit the tone of the tone of the tube. Well, and then there are also other acoustical reasons for having the horn, but that's one of them. And then in the case of a clarinet, just to finish on that, what happens is that so you have the mouthpiece, and then you have the reed here, right? And the reason why the reed vibrates at a specific frequency, depending on the length of the clarinet, or depending on the length of the tube, is because, so when you start blowing, you're going to create an impulse, right? And this impulse, so the reed is going to go up, like, so the reed is going to go up, it's going to close, and then the wave is going to travel in the tube, okay? Then it's going to be reflected, and then it's going to hit the reed. And it's going to hit it so hard that it's actually going to push the reed backward. And then, because you're blowing in the clarinet, once the reed is backward, just like a spring, it's going to go forward again. And that's how the reed is going to vibrate at a specific frequency. And because you're going to be able to change the length of the tube of the clarinet, this is going to happen faster or slower. Right? So if you have a very long clarinet, then it's going to take more time for the wave to go at the end of the clarinet and to go back and to push the reed again. And that's why the frequency of the reed changes in function of the length of the tube of the clarinet. So, yeah. Yeah?
If we wanted to make this open it as a polyphonic instrument, would we use the parallel function for that?
So that's a very good question. So with Faust, we consider, so Faust is considered to be a low or lower level programming language than like SuperCollider or all these programming languages. So we think it's better to not try to create the polyphony of an instrument directly in Faust. It should be done in the architecture file. So, so when you create an instrument that has the freq, the gate, and the gain parameters, so like the standard names for creating MIDI instruments, some of the Faust architecture files are automatically going to make the object a polyphonic object. So in general, you don't have to think about it. Not all the architecture files do it. And you can configure that at compilation time by using a flag and setting the number of voices of polyphony that you want, for example. But you shouldn't do it in Faust because the architecture file system does it for you, basically, and make your object a polyphonic object automatically.